I'm Troy McClure. You've seen me in such epic, quality chemistry educational videos such as Canu AP CHem Chapter 6 Review, Part 1, and There Are Thermoses in Thermochemistry, Part 4. Okay. I'm using a different format this time for the second part of the review because the first part of the review, the battery died on the camera and I could only get to this problem here. But that took care of a lot of the slides that you needed to be familiar with. So here we're going to be looking at calculating the standard enthalpy of combustion for the transition of carbon that's in the form of graphite to carbon that's in the form of a diamond, given those two pieces of information that you see on the screen here. Okay, I'm going to go ahead and rearrange this hat and go with it. I do have to put up my sponsor for this particular video. Oh, not that sponsor. That's this sponsor. Okay, I got you there, buddy. Okay, it's not every day I create AP Chem thermodynamics test questions, but when I do, I make sure they are challenging. Thank you for that. Now, back to our regularly scheduled program. Okay, so we're looking at going carbon and graphite plus O2 gets us CO2. There's our delta H of negative 393.5 kJs per mole. And they got CO2 becoming carbon in the form of a diamond plus O2, and we got a delta H of formation of 395.41. Now, if we were to go and look at these equations, given that we're starting with graphite and we're ending with diamond, again, you'll notice that we don't need to do a whole lot of anything because the graphite is on the correct side of the arrow. Okay, so we don't need to multiply by anything and we don't need to change the negative sign. Okay, remember negative means it's exo. All right. On the other hand, you've got CO2, all right, that is forming the diamond. The diamond is on the right side of the arrow. Perfect. We don't need to add anything to it. We don't need to multiply it by anything. So we can just add the negative 393.5 plus the 395.41, and then we would get the difference, which is like a little over 2.09 or something along those lines. It's kind of hard not doing it without a calculator on the paper here. Okay, but the idea that is per mole. Now, in addition to a problem like this could be like a good FRQ. What if I went ahead and I said, look, I need 2.5 moles of diamond. How much energy am I going to need in order to make it happen? And then you can just take whatever the difference is between those two, multiply it by 2.5, and that's going to be how much energy you're going to have to deal with when you get your 2.5 moles of diamonds. Okay? All right, let's go ahead and let's move on. All right, this is the one. Now, in this case here, we are given 3 different reactions and what the enthalpy of those reactions are. Okay, and then we say at the end at the bottom, it says calculate the delta H for 2 carbons plus hydrogen gas, and we get C2H2 gas. Okay. That's great. So that means we need to look at these 3 equations and see how that balances out. And we're going to have to do some balancing. Now, up to this point in chemistry, you may notice that you always worked with whole numbers. Okay? Because when we're looking at honors chem and regular chem, we can teach them that. Okay? And it does make it easier for balancing things. However, in this case here, this is accurate in that the ratios are still the same. Excuse me. Now, like the H2 plus 1/2 O2 gets us H2O. The ratios of oxygen and hydrogen on both sides of the arrow, it's still the same. Okay? That's okay This is done basically for the enthalpy, and that's it. For our purposes here, for AP Chemistry, if you go on to college and take, other chem classes, then they get to do whatever they want. All right. So in this case here, let's take a look. We know that the C2H2, we need to have it on the right side of the arrow, as you can see here on the bottom. As I move over here, it's like, yeah, you're on the right side. But we kind of notice that our CH2 above my head here is on the left side. So how do we solve that? Well, if you notice over here where it says negative 1300 kilojoules, we're going to need to flip the equation around. We're going to have to flip it. So if we're going to flip it, what's going to happen to the value? Is it still going to be negative 1300 kilojoules? Why, no, it's not. It's going to be plus 1300 kilojoules because we are reversing the order of the reaction. Okay? Remember, we are working with Hess's law and the heat of summation. Now, what about the CS? Do we need to do anything about that? Yeah, we do. Because do we need to change the direction that it's going in? No, we don't. Why? Well, because the CS that's over to my right, the right of the picture, is on the same side of the arrow as our final equation over there. So, but here, if you notice, we got 2 CS. So that means we're going to have to take this delta H of negative 394 kilojoules and multiply it by 2. All right. And then our last one is the H2O plus 1/2 O2 gets us H2O. Do we need to change directions? Nope. Do we need to multiply by any numbers? Nope. So, then we just simply add them up, and that's it. Now remember, if it's negative, it's exothermic. If it's positive, it's endothermic. Okay, let's move on. Okay. Now remember, the idea when we go and put these all together, that we're going to be canceling out this stuff. If you're still trying to figure out how to do that, I do have videos on that. You'll have to look. It's Canu AP Chem, Hess's Law, Parts 1 and 2. I do work on 2 separate problems, but I do spend more time and go into detail. Okay? That is without the Odell effect. Okay? Just making sure. All right, let's go on to 33. Standard enthalpy of formation. Okay. It still has Hess's law. It's just with standard enthalpy of formation, instead of looking at the individual steps of the reaction, we just simply say, oh, okay, this is how much enthalpy of formation it's going to take to form 1 mole of H2O or 1 mole of C2H2. That's basically it. Okay? Let's see. What other things do we have there? Okay, so the symbol of our standard enthalpy of formation is delta HF. Delta, of course, is the change, the degree. It tells us it's a standard enthalpy change. F is the reaction of a substance. That's 4 information elements. I'm sorry, I'm kind of tired. It's what happens when you work with second period AP Chemistry. But yeah. All right, delta H of the reaction. This is going to be a little bit different. We're looking at the summation of the delta H of the products minus the summation of the delta H of the reactants. So that's going to be a useful thing that you're going to have. Will I give you that formula on the test? Yeah, sure I will. Okay, standard of the enthalpy formation, okay, is just summing up what we said in the last thing. So Hess's law, of course, it makes a difference when you know a bunch of reactions, okay? But remember, I will give you the information of the standard heats of formation. Now, typically that's for like 1 mole of something. Now, what are the conditions for the standard states? 1 atmosphere, 1 molar, and 25 Celsius. All right, as we go through. Now, for an element, it's 0. Well, what do we mean by for an element, it's 0? If we're looking at the enthalpy of formation of O2 or the enthalpy of formation for H2, okay, guess what? That's going to be 0. Why is it 0? Natural state. It's the natural state you find hydrogen in. It's the natural state you find oxygen in. That's basically it. Now, sorry. What about O3? Well, O3 is not the natural state of oxygen, even though it's 3 oxygens and it is a gas. Okay, it is ozone for all you apes fans out there. But the truth of the matter is O2 is the natural state that it's in. So we can go from there. So for an element, it's going to be 0. Now, there is a table. I would provide you that information. On the AP exam, they would provide you with that information. Let's move on. Okay, so I got to move on here. All right, so there's an example for you guys to work through. All right, I did create a standard enthalpy of formation video. Look that up under Born to Tag on YouTube. You will find it. It is there. Not many people have viewed it. Take advantage of it. I work through and explain the examples. Okay, here we go. As we go to the end here, of course, the idea is you need to be able to write the equations. Excuse me. Again, what's the equation for the formation of NO2, for example? This is, again, where we can use the fractions. 1/2 N2 plus O2 gas gets us NO2. Have to make 1 mole meet that definition and write the equation for the formation of methanol. And that's just the problem, which, again, you guys can go look it up. Okay, so okay, we can mess around with the equations, that's great. But you know what? We can use the heats of formation to figure out the heat of reaction. You say, wait a minute, you're using heat! What? What's happening? We're being invaded by aliens. Okay, don't freak out. When they say heat of formation or heat of reaction, it's basically the same thing as delta H. Enthalpy! Okay, yeah, it's the same. And my time is running out. So let's do it with this equation here. Well, we need some pieces of information there. So this is our final formula here on the bottom. The summation, that's what that sigma is, the summation of the delta H of the formation of the products minus the summation of the delta H of the formation of the reactants equals the total delta H of our reaction. And with that, ladies and gentlemen, there are videos that you guys can watch, and I hope this will help you guys out. Until then, you guys take it easy and take care. Bye.